welcome to Lessons in Logic number 40, if I'm not mistaken. We're already up to 40, and I don't know how many we have left, but we'll probably break 50. So this is Grassy Hill in Hong Kong, a bit of natural beauty before we move to the beauty of logic. We're looking more or less eastwards. It's hard to be more specific. Things are not usually at right angles in Hong Kong. I hope I haven't said this already, but I think I may not have kept a video in which I said this. In any case, if I did say it, I'm saying it again. This is a beautiful place, and here's a picture of it. And now let's send most of it away and just keep bits of it in the background while we look at the beauty of logic. All right, proofs using equivalence rules. All right, so page 313, probably of The Power of Logic, says something about the number of rules in a proving system. I'll just paraphrase what I imagine it says, though I don't have that book on my shelf at the moment. What it says is probably if you have more rules, you can apply them more easily to more situations, but you also have more rules to keep track of, so it's difficult to know exactly how many rules you need. Somewhere, someone has come up with the minimal number of rules. In fact, I've probably read about it myself. It's probably not that difficult to have a lesson on it in a logic textbook. In fact, there's a very good chance I'm thinking this because I've read it in a logic textbook lesson, but I'm not doing that. It is possible to find the smallest number of rules. Some of these things will simplify. Some of these things will make it easier to apply the same things that could be done with extra steps. Never mind. The important thing is there's some minimal number of rules you need to be able to do a proof for any valid argument. And we probably have more than that, but the extra ones we have make it a lot simpler to apply things. But having too many of those means there's more to keep track of. And in any case, let's just go with what we have. What we have is good, inspired, I think, mostly by The Power of Logic by Lehman, Wasserman, Howard Snyder, and Howard Snyder. And here we are looking at some new rules. We are calling these the equivalence rules. Now, these rules are based on certain statements being logically equivalent to each other. Maybe I should say certain statement patterns making statements logically equivalent to each other. And it's pretty simple and perhaps even obvious how some of this works. If a statement, actually, never mind whether it's true, that doesn't even matter. What matters is a statement is equivalent to the negation of its negation, the denial of its denial. If I say Mark has an empty teacup, and then I say it's not the case that Mark does not have an empty teacup, that is the same thing. Those are the same claim. It's not the case that it's not the case means the same thing as it is the case. Commutation. Well, this just tells us you can switch around the ordering of statements when it's a simple either or both and. Mark has an empty teacup and an empty peanut jar. Mark has an empty peanut jar and an empty teacup. Mark has an empty peanut jar or an empty teacup. Mark has an empty teacup or Mark has an empty peanut jar. All the same thing. Association, pretty much the same thing. This, in fact, is just a grammar thing, really. As we discussed in an earlier video, you need to have parentheses so you know exactly which statements a symbol is operating on. The either or symbol here, this wedge, and the dot symbol here, the both and symbol. Each of them operates on a statement to its direct left to its direct right. So if you had no parentheses here, it's not clear whether you're saying P or Q or R, or whether you're saying P or Q or R. Now, it makes no difference with this particular statement, which is why we have these association rules. Change around the parentheses, you don't change the meaning. But it would make a huge difference if we had something else here, for example, a dot. Anyway, you have to have the parentheses for good grammar, which avoids massive quantities of ambiguity. We can't allow any ambiguity in symbolic statement logic. That's bad. Ambiguity needs to go away, make it go out of here and make things clear and precise. But that does not mean that the parentheses change the meaning of every proposition, and hence open parenthesis P wedge open parenthesis Q wedge R close parenthesis is logically equivalent to open parenthesis P wedge Q close parenthesis wedge R close parenthesis, etc. All right, so I haven't mentioned the try-bar yet. Now, I think in some different contexts, you'll see a try-bar. In some cases, you'll see 4 dots. I'm not going to elaborate on any subtle distinction here. I think for our purposes, this is just fine. But no, there may be slightly different symbolization systems in different textbooks and things. My notes actually told me to get 4 dots, and honestly, I didn't know how, so I'm going with the try-bar. I think it works just fine. I think it's a system some people do use. These 2 statements are logically equivalent. Any statement and its negation. It's double negation. P wedge Q, any P, any Q. P wedge Q for any P and any Q is equivalent to Q wedge P for any P, any Q. Bearing in mind that P and Q here symbolize any statement. All right. Now, De Morgan's, this one is fun, and it might require just a bit of thought, but it's also very straightforward. It doesn't require much thought. Tilde open parenthesis P dot Q is equivalent to open parenthesis tilde P wedge tilde Q close parenthesis, and tilde open parenthesis P wedge Q is equivalent to open parenthesis tilde P dot tilde Q close parenthesis. Meaning, if I say it is not the case that Mark has an empty teacup and Mark has an empty peanut jar, that's the same thing as saying either Mark does not have an empty teacup or Mark does not have an empty peanut jar, and vice versa. Remember, these can go either direction. With these logical equivalences, you're allowed to go from a double negation to the proposition doubly negated, or vice versa. With commutation, you're allowed to switch P and Q around. I guess that doesn't make a difference there. You can move the parentheses anywhere you want with association, as long as you're doing it consistently with the form. You can go from left to right or from right to left with respect to which side of this try-bar you're starting on and which you're finishing on. Okay, De Morgan's. What was the other De Morgan's one? If I say it's not the case that Mark has an empty peanut jar or Mark has an empty teacup, that's the same thing as saying Mark does not have an empty peanut jar and Mark does not have an empty teacup. As it happens, they're both empty at this time. How unfortunate. Contraposition. All right, this one's kind of cool. P horseshoe Q or P arrow Q. We switched over to arrows because those were the symbols I had in my notes and it doesn't make much difference. Sorry for any confusion. P arrow Q or P horseshoe Q means tilde Q, arrow tilde P, or tilde Q, horseshoe tilde P. So these are logically equivalent. If it is raining, then I should bring an umbrella. It's logically equivalent to, if I should not bring an umbrella, then it's not raining. Think about it if you like. You should find they mean the same thing. Or if that's difficult, think back in terms of what we talked about earlier on when we were introducing symbolization systems for statement logic. They're always going to be true and false, true or false at the same time. If it's true that if it's raining, then I should bring an umbrella, then it's true that if I should not bring an umbrella, then it's not raining. And if one's false, the other's false, and vice versa. They are true and false in exactly the same circumstances. Now, before we go over any illustrations, which is probably what you need more than anything here, let's give some quick advice. This, I think, is based on mistakes I've seen students making in homework. Don't skip steps. Double negation D to D needs a step. You need 2 disjunctive syllogisms steps. Wait a minute, disjunctive syllogism. F till F horseshoe H horseshoe Q horseshoe Z. This should not say DS, these should say HS. Okay, so I've seen students skip steps. To give one example, let's separate these examples because there's too much going on. There we go, much better. Don't skip steps. You need a separate line of a proof to get from double tilde D to D, or vice versa. And then if you have F arrow H arrow Q, and Q arrow Z, you can't go straight to F arrow Z. You need to first go to F arrow Q, combine those first 2 arrows, or go from H to Z, H arrow Z, combine those 2 arrows. You have to do one of those 2 first, and then you can go straight to F horseshoe Z, F arrow Z. You have to have 2 hypothetical syllogism steps. Cite the correct number of steps. Look at the number of steps required to make an inference in one of the rules. That's the number of steps that needs to be cited when you use that rule. So remember, modus ponens has the modus ponens rule has the pattern P arrow Q, P therefore Q. Modus tollens rule has the pattern P arrow Q, tilde Q, therefore tilde P. And that means two premises should be cited for each inference, two premises, and then implicitly the third step of the rule is the inference you're making, but never cite that inference. You're citing the premises that get you to a conclusion. Remember, in a proof, we have a set of original premises, and then we're trying to get to the final conclusion, and every step in between is a sub-conclusion. It's a conclusion with respect to the original premises, but if we need it to be, it's also a premise with respect to the final conclusion. And a step should never cite itself. With proofing, we follow rules that have certain patterns. We look for premises that fit those patterns, and then we draw the conclusion that fits the pattern likewise. I didn't say that very precisely. Let me try it again. When we do proofing, we look for premises that fit the beginning of a pattern, then we draw the conclusion that fits the end of the pattern. So the beginning of the pattern for the modus ponens proofing rule is P horseshoe Q, or P arrow Q, P, and then the conclusion you can draw from that is Q. So you look for premises that have the statement, if statement, then other statement, and then statement. The if statement occurs in its own separate premise. If you have a premise that says if statement, then other statement, then that first statement occurs by itself in another premise, then you can cite those two and conclude the second statement. If X, then Y, X, therefore Y. So the thing that comes after the therefore, the inference rules from 2 videos back, the thing that comes after the therefore is the conclusion of a step in a proof. Maybe the final conclusion, usually a sub-conclusion. And what it cites is the steps that have the pattern of what comes before the therefore in the inference rule. Now, for these rules, you only cite one step for each rule. Double negation should always cite one step. Modus ponens should cite 2 steps. Constructed dilemma should cite 3 steps. And a step should never cite itself. And above all, as I emphasized in the former video, the last video, 1 week before this one, every rule has a certain form, or I prefer to say a certain pattern. Look for steps that fit the pattern of a rule and draw the conclusion that follows the same pattern. Once again, modus tollens has the pattern if P, then Q, not Q, therefore not P. So look for steps where you have a premise that says if something, then something, and another premise that denies the second something, and then you can conclude with, you can make a conclusion that is the denial of the first something. If X, then Y, not Y, therefore not X. Find an if X, then Y premise, find a not Y premise, bring them together, citing the modus tollens rule to conclude not X. All right, now let's practice, and then I suppose we'll be finished with this video. And then I think in the next video we'll do another nice slow look at the patterns we're working with. All right. If A, then not Z, Z therefore not A. Now, what you're tempted to do, if you're like me and many a logic student, you're tempted to go from Z to the denial of A directly with the modus tollens step. So you're tempted to apply modus tollens to premise 1 and premise 2. Modus tollens having the pattern P, arrow, Q, tilde, Q, therefore, tilde P. You're tempted to do that, but you can't. You're skipping a step because the Q, in this case, is tilde Z. So we don't have a tilde Z. Sorry, we don't have a tilde tilde Z. We need to deny tilde Z, which means we need tilde tilde Z. We don't have tilde tilde Z as is. So we first have to add tilde tilde Z. And you're thinking, well, yeah, but we already have it. And I'm thinking, well, yeah, but a proof is a series of steps that proves that we have it. Prove that we have it. Don't just skip over while assuming that we have it. Prove everything. That's the point of a proof. Prove every dang step. Now, if we had a separate proofing rule, this is a great illustration, actually, the number of rules. We could have had another proofing rule that allows us to go from P, arrow, tilde q and q to tilde p. That would have been a great rule, except we just don't need it. It's better to just be prepared to use the double negation rule when we have it. We could have called that rule modus tollens variation 1 or something like that. And we could have come up with some other variations of modus tollens. It would have been fine, but it would have been an unnecessary rule. Here's where we use 2 steps to accomplish the same thing, and we don't have to remember an alternative rule. Here is how to do this proof properly. First, conclude by double negation on premise 1, tilde tilde z. Then, remembering that q, when it's lowercase, we're looking at the form of something, the pattern of something. Q can refer to any statement, refer to an atomic statement like z, or to a negation of an atomic statement like tilde z. We apply now modus tollens to lines 1 and 3, giving us tilde a. Okay, so the modus tollens pattern is if P, then Q, not Q, therefore not P. So here our P is A, applying that pattern. Our Q is tilde Z. And we have a negation of tilde Z in our third premise. So A is P, or A corresponds to P in the modus tollens pattern. Tilde Z corresponds to Q in the modus tollens pattern, and that allows us to conclude what corresponds to tilde P in the modus tollens pattern, which is tilde A. I don't know how to say that more clearly. I think I said it about as precisely as possible, and if you got lost in it, then pull up modus tollens pattern, rewind to the 2 videos back where I introduced modus tollens pattern, look at it, see if you can see it. Let's do this one now. This should be fun. At least I thought it was fun when I was setting it up a while ago. I think, yeah, let's employ the Mike Beatty of Baylor University strategy here. Let's do a quick strategy session and see how we're going to work backwards. We're going to use double negation as our last step to get from tilde tilde z to z. That seems pretty obvious. There's nowhere else z even appears in the premises, which means in order to get to tilde tilde z, we're probably going to have to affirm x or y. How are we going to get x or y? Well, I can see how we're going to get it, but I'm not sure I can explain it very well. I can do the proof. Briefly, I think what we're going to do is we're going to get x or y by some clever motion that allows us to get either tilde h or tilde u. Then we're going to do a constructive dilemma. So if that didn't make sense, this is actually one where going straight through it is actually pretty safe. Well, I do normally recommend the Beatty rule of working backwards, but we've done as much as we can in this simple video. Let's go straight to working through it because I can tell you it's going to work out just fine. What we're going to do first is one equivalence rule in particular, and what we want is De Morgan's. De Morgan's allows us to make these inferences from something following this pattern to something following this pattern, or vice versa, or from something following this pattern to something following this pattern, or vice versa. So this follows which pattern? Which of these 4 does it follow? Here's a little set of 4 boxes. Which box does tilde h dot u fit? See if you can figure it out. Pause the video if you need more time to think before I give you the answer. It is not this one or this one or this one. It fits this box. So it's going to give us this box and follow the pattern. From here to here, it's a terrible looking arrow, but using capital H in place of P and capital U in place of Q. In other words, what we want is just to do a De Morgan's on line 1, giving us tilde H or tilde U, because if it's not true that H and U are both, if it's not the case that H and U are both true, then one of them is false. And that's what we're doing, and it's a De Morgan's on line 1. Now, probably we're not going to look at line 1 again for the duration of this proof, and probably we're going to use line 5. Now, I think actually we can go directly to using line 5, and I think, yes, I think it's actually fairly clear at this point. Our next moves are going to be a simple, our next move is going to be a simple constructive dilemma. The constructive dilemma form is P or Q. If P, then R. If Q, then S. Therefore, either R or S. And here we're going to use tilde H for P, tilde U for Q, X for R, Y for S. In other words, by constructive dilemma on lines 4, 2, and 3, make that 5, 2, and 3. By constructive dilemma on lines 5, 2, and 3, we can go from either not H or not U, and if not H, then Y, and if not U, then Y, to either X. What did I just say? I think I botched that. Let's try that again. By constructive dilemma on lines 5, 2, and 3, we can go from either not H or not U, and if not H, then X, and if not U, then Y, to either X or Y. So now, I don't think we're going to use premise 1 or premise 2 or premise 3 or step 5 again, which means we're one step away from the end. We're just going to use 4 and 6. Now, do you see? Now we're 2 steps away from the end. We are so close. We're going to use 4 and 6 to get to our final conclusion. Do you see how to use 4 and 6 to get there? It's our first rule ever. Remember, when we're using those lowercase symbols, remember our modus, let me just type it up for you. Modus ponens rule looks like this. Let me remove that scratching out, because it's a bad habit to do that for long. I don't recommend doing it on written homework, but we're looking at this. We're only going to use 4 and 6 to get to our final conclusion here. And it is going to take, I'm afraid, 2 steps, but we're going to use modus ponens here. And the modus ponens rule looks like this. Modus ponens rule looks like this. If P, then Q, sorry. There we go. Modus ponens rule looks like this. If P, then Q, P, therefore Q. And remember, these lowercase letters, P, Q, can stand for any statement they need to, atomic or otherwise. So in this case, P stands for X or Y, which we have right here now in step 6, which means we can apply modus ponens very simply and get tilde Z out of lines 4 and 6. And now all that's left, the only things we haven't used yet, is a nice orderly proof, no statements that trip us up. The only thing we haven't used yet is 7. We haven't quite got to Z. We need to get from tilde Z to Z. Now, the rookie logic student says, I'm done at this point, but you're not done at this point. You have to show that Z precisely follows from these premises. So it's a simple double negation step. Let's see, tilde Z, therefore Z. By double negation, on line 7. And that's it. We're done. Yay, that was a nice proof. All right, one more. And let's see if I can go a little bit faster. Something is amiss with the formatting or something here. Okay, so we're trying to get from not S or R with parentheses around S or R, tilde open parentheses, S wedge R close parenthesis as one premise, and from another premise, open parenthesis, P dot G, close parenthesis, horseshoe R. We're trying to get from that to tilde G wedge tilde P. We're trying to get from the denial that either S or R is the case as one premise, and from another premise, if both P and G are the case, then R is the case. We're trying to get from those premises to the conclusion either G is not true or P is not true. Now, how the heck do we do that? Well, let me just do a quick Beatty rule working backwards. Tilde G or tilde P. Well, off the top of my head, I just don't even know how to get to that. So let's not try that strategy. Not always will working backwards help. It's usually a good rule. In fact, it's probably always a good rule to try. But at the moment, I'm having trouble even seeing how I'm going to get that. So I'm going to look at the proof and look for another strategy here. Now, I can easily see why I set the proof up this way. Now, I hope I didn't make some terrible mistake in setting up a proof here. I can easily see that I probably wanted to apply De Morgan's. And it's easy to see you could apply De Morgan's. That'll give you not S and not R. And now I see what the strategy is. This is very simple. Okay, let me tell you the working backwards strategy. Not G or not P means not both of them. With this simple rule, I want to say it's commutation. My brain tried to make me say transposition, so I'm glad I scrolled up and didn't let myself. Transposition is a totally different rule. What we want here, actually, I want to say transposition. I better check my notes. I said this is contraposition. My brain is telling me, no, it's transposition. But my brain was also telling me to say transposition up here. And commutation is the rule I want. So I'm mentally noting that I should check up on the name of this rule. My brain is telling me I have the wrong name typed up here. I wouldn't put that past me. Okay, commutation allows us to switch around the order of a wedge or dot statement. Either X or Y can be switched around to either Y or X. X and Y can be switched around to X or Y. So our conclusion is going to be a statement that either G or P is false. Switch that around, and it can mean by that rule, by commutation, either P or G is false. Now, how do you get to either P or G being false? Let's see, I want this in blue. How do you get to either P or G being false? We're going to use a commutation to get to the conclusion. But how do you get to either P or G being false by the De Morgan's on P dot G? If P and G, if the combined statement P and G, both P and G, is false, then either P or G is false. You see, we are going to deny P dot G, and that will give us not P or not G. And then we're just going to commute that around to not G or not P to get to our conclusion. So how are we going to deny this? At this point, it should be a lot easier to see. We're going to deny P dot G by denying R. How are we going to get R? From the first premise. And what can you do on the first premise? Just looking at the first premise, you might even be able to see it. We're going to do a De Morgan's on the first premise. And after that, I think everything will come through very simply. Let's do a De Morgan's on the first premise. That tells us not S and not R. On premise 1, De Morgan's, tilde S dot tilde R. And now that we have tilde R, we can use it to do a modus tollens on line 2. But first, we have to get it by itself. You have to separate it. Now, this is, what do we call this? We did this last time. This is simplification. Do a simplification step on line 3. And that gets you tilde R. Now, this is going to be a nice, simple, neat proof. We're not going to need to reuse any premises. So we've already used that, and we've already used that. We're not going to need them anymore. Now we're going to get to our conclusion just by using statement 2 and statement 4. So I think we're going to need an extra step. Statement 5 will probably also be useful to get us to statement 6, which might be our final conclusion. Or maybe there's another one. I can't think fast enough. I don't know what button I just pushed. There we go. So now statement 5 is going to use 2 and 4 to get to something exciting. What's exciting? if P and G then are, tilde are therefore not P and G, but don't write it the wrong way. Remember those parentheses. Not P and G, like this, is very different from not P and G, like this. Now that was a modus tollens on lines 2 and 4. Let's make sure that looks right. Line 2, line 4. Applying modus tollens, P dot G, arrow R, tilde R, therefore tilde, P dot G, everything looks fine. So now we've used this premise, and I don't think we're going to use it again. We've used this one. I don't think we're going to use it again. We've used this one. I don't think we're going to use it again. I think we've even used this one. Yes, we just used it. I don't think we're going to use it again. We're going to now get from statement 5 here to our final conclusion without looking at anything else. Now, what can you do with statement 5? All you have is statement 5 to work with here. I mean, you could try something weird using other premises, but please don't. It's not going to do you any good. How do you get from statement 5 to that conclusion? Very simple. Do another De Morgan's. Tilde P wedge tilde G by De Morgan's on line 5. And then you're basically there. You just have to do one simple step. It's that other one my brain was trying to misname. It's commutation. Commutation on line 6 will get you to your final conclusion, and we are finished with that proof. And now, being finished with the proof, let's now finish with the video and state that let's finish the video by fixing one thing. I don't remember why I have this typed up here, honestly. I think we don't want this. Let's rename this rule. We want to call this rule transposition. Now, there are different names for different rules. I can't promise that you won't find a different rule for this name, or a rule called contraposition. And I don't think I have any logic textbook even in my office right now, so it's difficult to check the formal list of rules from my preferred logic textbook, which I don't even have a copy of at the moment, which is a real shame. But anyway, you will find different names for different rules, and it's okay to get confused. I get confused, obviously. Pathetic, isn't it? But transposition is a good name for this rule, and I think it's the conventional name for this rule. But the rules names don't matter all that much. What matters is you have a set of rules, and you know how to apply them, and you're following the rules stipulated for whatever logic class you're in. So if you're in my logic class, that is to say, if you're not taking any logic class anywhere else, if you are, follow the textbook for that class. Use me to explain some of the concepts and to illustrate the strategies and so on, but do not take my abbreviations, my names for the rules, my style of doing things. If you have 4 dots instead of the tri-bar, if you have a horseshoe instead of an arrow, or an arrow instead of a horseshoe, then ignore my use of arrows and horseshoes, since I've used both in this series. Anyway, I think this is a better name for the rule if you don't have another one in place. But stick with the conventions of whatever you're working with. And if you're only working with this, then I recommend using the name transposition for this rule. All right, I think we are finished, and I'll see you next time. And what we really need at this point is a nice bit of slow practice with some of these equivalence rules. But now that I think of it, we might need more lessons before we're even ready for the slow practice. So we might do conditional proofs. We might introduce conditional proofs in the next video. We'll see. See you then.